Next, we'll look at two higher order functions, map and reduce. So let's look at reduce first. Reduce is a procedure that takes another procedure, some list S, which we're going to iterate over, and then a starting value. And what it does is it combines the starting value with the first element of S, combines that result with the second element, etc., using the procedure to combine them. So if we reduce with the multiplication procedure, the list 3, 4, 5, starting with 2, then we'll get 2 times 3 times 4 times 5 is 120. And if we reduce using a procedure that takes two things and conses them together, y first then x, with a starting value of the list containing 2, we'll then cons on 3, then we'll cons on 4 to that, then we'll cons on 5 to that. Consing a number with a list gives you a longer list with the number in front. So the entire result will be 5, 4, 3, 2. Okay, let's look at the definition. If S is null, then we just use the starting value. Otherwise, we reduce, with the procedure, the rest of S, though we need to create a new starting value, which is the procedure that was passed in, called on the starting value we had before, and the first element of S. So in this way, we create a new starting value which already includes not only what we started with before, but also the first element of S. So in this case, we'll start with 2, but in the next recursive call to reduce, we'll have 2 times 3 is 6. And in the next one after that, we'll have multiplied in 4 to get 24, and eventually 120. So let's take a look. This whole thing is a tail context, which means this is a tail context. But this is not. So does the whole thing run in constant time? Well, it really just depends on what the procedure does. So the recursive call to reduce is a tail call. But the other call, in particular, the procedure call, is not. And this is a higher order function, so we don't know what procedure will be passed in. So the total space of reduce will depend on whether the procedure requires constant space or not. Hopefully it just requires constant space, in which case the entire reduce will require only constant space. Okay, now let's talk about how to map with only a constant number of frames. Map is a function that applies a procedure to every element in a list and constructs a list containing all of the results. So let's come up with the most natural version to define map, and then we'll kind of come up with a tail recursive version. So a natural way to define map is to say we take in a procedure and a list S. If S is null, we return the empty list. Otherwise, we're going to create a new list where the first element is whatever we get by applying the procedure to the car of S, to the first element of S. And then the rest of this result will be what you get when you map the procedure over the rest of the list. So for example, if I map a function that takes each element and subtracts it from 5 to the list 1, 2, under this definition, which is not tail recursive, we start out with the list 1, 2. We bind it to S in the first call to map. The second call to map takes the rest of S, and the third call takes the rest of that. Now the final result of returning from the third call is just nil, but the second call returns a list that starts with 3, and the third call starts a list that starts with 4. So 4 is 5 minus 1, and 3 is 2 minus 1, and that's what we're computing here. So this is not tail recursive because we have a tail context for all of if, but within cons, which is in a tail context, we have a sub-expression that's not in a tail context that calls map. So here is a tail recursive definition of map. Not what you would expect. Define map by computing the reverse of the map, meaning exactly what we want, but in the reverse order. This first checks if S is null. If so, we return the result, which is the mapped list in reverse that we've already constructed, M. If it's not null, then we have more work to do. So we call map reverse on the rest of S. So that's everything else we're going to work on. And what we're going to do is we're going to cons on the next element of the resulting mapped list. So we cons on the result of calling the procedure on the car of S. And what's the rest of that? Well, that's the M we've constructed so far. So we're going to start out with a nil. We're going to add the 4 on first, and then we're going to add the 3 on, thus giving us our list in reverse order. So finally, we need to call reverse on map reverse S nil. Now, is this a tail context? Well, this whole thing is in a tail context, so the call to reverse is. This call is not. But notice it's not a recursive call to map, it's a call to map reverse, which is a tail recursive procedure that runs in constant space. Now what about reverse? Well, we need to make sure that that's tail recursive too. So here's a definition of reversing a list. We define reverse iter, which takes S and the reversed list so far. And what we're going to do is cons on a reversed version of S to R. So if S is null, then we just have R. Otherwise, we call reverse iter on the rest of S, consing on the first element of S onto R. So think about it for a minute. You'll see that this will reverse the list if I just start out with nil as my reversed list and S as the thing I'm reversing. So this is one of the more complex examples of making a procedure tail recursive. There were 2 steps we had to figure out how to make sure that we can build up something that maps over the elements of S such that we collect all the results, and then we realized, well, that would build it in the reverse order because as you are building up the recursive list from the back to the front, you're processing the input from the front to the back. And so then we had to define reverse in order to give us exactly the result that we wanted.